So let's take up a topic which is signal flow graph representation. Okay, signal flow graph representation of in a DSP system. Okay, signal flow graphs. So what it does is like if you look at the DSP of major calculations involved in DSP, right? One of them is just think about a calculation where like x of n is represented as think about a into x of n minus 1 plus b into x of n minus 2. Okay, so think about like this is what it is. So what it will be, the major components in a DSP when we are dealing with DSP equations. One is this delay elements. Okay, one is a delay element. These are the delay elements which you have. Okay, when you delay a certain sequence. The other one is the multipliers. Okay, the scalar multipliers you have. Okay, scaling, you can say scaling. And the third operation which you have is basically the addition. Okay, the addition. So these are the three major operations that you will see in a DSP with respect to the digital signal processing. Okay, any processing of signal will involve these particular operations. So you represent any this kind of let's say you are given this kind of a equation, right? So how do you represent this? One way you do that is you have this as x of n which is coming in. Okay, let's say this is a point which is x of n. Okay, so one way of doing this is you delay this. So think about like this is not the case. Okay, so let me just rewrite this equation. Let's say this is y of n is given as plus c into x of n. So let's say this is your equation which you have. With the one previous one was like similar to feedback equation. So let's talk about it later. So right now we'll consider this. Okay, so you have this kind of a equation which is there with you, and I want to represent this using signal flow graphs. Okay, so if I want to represent this particular equation using a signal flow graph, how I'll do that is you have x of n as the input. Okay, there is an input which is x of n, and that gets, when you scale this with a c, what you get at this node is c into x of n. Okay, this is one way of one component of showing your signal flow graph. Okay, next thing, right, we always use this like with respect to when you are taking a z transform, the delay elements y of z will be equal to, when I take a z transform of this guy, if you have a x of n, let's say you have x of n which has got a z transform of x of z, right? X of n minus 1 will have a z transform of z inverse into x of z. Okay, so a delay element is always represented by multiplying a z inverse. Okay, so let's say this guy x of n. Okay, I multiply this with a z inverse. What it will mean is, the moment I multiply this with a z inverse, I know that this is going to be like given by x of n minus 1. Okay, so this is what it means. So if I multiply this by a z inverse, this is basically I am adding a delay element here. So this is in the signal flow graph representation. So yeah, so then another one is when I am trying to add, let's say x of n. Okay, and there is, this is coming straight into c. Okay, whereas this guy I delay it z raised to minus 1, so I get here x of n minus 1, and then I multiply this guy here with a b. So what you will get at this particular point is c into x of n plus b into x of n minus 1. This is how it is. So the third branch for this guy, you know that the third branch is a so b into x of n minus 2. So let me just change this. This will be a, this will be a here. So this guy is scaled by a. Okay, this guy is scaled by a, plus now I got to add b into x of n minus 2, right? So I can, one way of doing that is I could have done this guy delayed by another z inverse and I add it here. So this is my x of n minus 2 and this is my scaled by b. So I could have got this, the expression at this node is y of n, which is c into x of n plus a into x of n minus 1 plus b into x of n minus 2. So this is a signal flow graph representation. So I wanted to represent this. So anything, let's say this is x of n, the multiply by a, I get a into x of n. Same way x of n, and you have, let's say, another one which is x1 of n. Okay, there's another signal. And when I have this kind of a signal flow graph representation, this is coming in, this is coming in. Okay, this is the arrow here. Okay, so let's say this is the arrow which is coming in here. Both converge at this particular node. So the value at this particular node will be x of n plus x of n minus x1 of n. Okay, so this will be the signal at this particular point. Okay, same way you have x of n. If I multiply this by z inverse, okay, I get x of n minus 1. Okay, clear? So this is about it. This is a signal flow graph representation. Then there is the same thing with a block diagram. This is a signal flow graph representation, and there is a block diagram representation which is, let's say this is x of n. If I want to multiply by a scalar, this here will be a into x of n. So this is a scalar component which I am multiplying. Okay, so how do you draw that? Is you draw a triangular block and scale it. The value of this scalar will be a. So same way, x of n, you pass, delay it, and what you get here is x of n minus 1. And if I want to add two signals, then this will be x of n, there will be a adder, and this guy coming in is x1 of n. I add these guys here, so the output here is x of n plus x of n minus 1, x1 of n, x1 of n. So this is a block diagram representation. This is a block diagram representation. So these are the operations which are commonly found in your signal processing course. Okay, so this will this is what I would like you guys to at least go through, so that in your FFTs I'll be using signal flow graphs, so the understanding is there when you take up that particular topic. So this one is a scaling operation, this one is adding, and this one is a delay. Okay, these are the three operations that you see in signal flow graphs. Same way in block diagram representation, this is scaling, okay, this is delay, and this is adding. Okay, so these three operations, clear?